Let's get started. Okay, so unfortunately, I've lost my stylus pen for my uh, laptop. So I think I need to use this Wacom display. So I will use where is the annotation? Hmm? Hmm? So annotation 없어? Wait a second. So I will use the annotation tool on Zoom. So so it is inconvenient actually. So okay, so in the previous class we learned about how the function is called, right? And then in order to support the function call, the RISC-V provides the jump and link instruction, right? So so when a function is called, then the the CPU, actually the CPU needs to change the program counter value to the first instruct, the program count of the first instruction in a function, in the target function, right? And then we can jump to the target function. And then I also mentioned that actually after the function is complete, then we need to return from the function, right? So the return address, the return PC actually, the return address is also need to be stored. The return address is stored in the RA, right? And then also we learned about the stack, right? Stack is the temporary memory space for storing the data, okay. So when a function is called, then the function may uh, override the required data in registers. So these required data need to be preserved. So those data are stored in stack, right? And so stack needs to be managed. So stack memory is managed using stack pointer, SP, right? So that's those are what we learned in the previous class. So and then so we so actually let's learn about the recursive function. So it's not reactive. Okay, so actually I in the previous class I briefly explained about this function, right? This is the factorial function. So this is the recursive function because the fact function calls its own fact function, right? But the argument is changed. Okay. Then I mentioned that we can write the assembly code based on this function form, right? The statement in a function. So if you see this if statement, so you can uh, implement the if statement using BGT, right? And then based on the condition, uh, okay. Oh, what? So it's not convenient. Okay, so based on the if condition, then we can call the other function. Also, the function complete its operation and then return to the caller function, right? So BGT. The BGT is the if statement. So if this condition is true, then it jumps to the else, right? You can find the else here. So, and then also you can find the else, else, then it returns the n multiplied by the return value of fact n minus 1, right? So what is required? We need to provide new argument to the fact function, right? So the A0 is updated, right? Oh, it's A0 is updated. So we just perform the n minus 1, and then we just call the fact function, right? The same function. Then it will also perform fact n minus 1, right? So, and then, so then we can return from the function, and then it is multiplied by n, and the return value is multiplied with the n, and then also it returns to the caller. Okay, but so in this example, the fact, so this fact function also calls its own fact function, right? So what are need to be what what the, what to need to be preserved? Okay, so in the else statement, so this fact function calls fact n minus 1, right? So argument is changed. So it calls other function. So what does need to be preserved? Stack pointer, right? No, not stack pointer. The array, return address, right? Because this is non-leaf function, right? So we learned that in the non-leaf function, when this function calls another function, then return address needs to be preserved, right? Also, so in this example, you can find that n is used here, but the argument is updated with the n minus 1. So which means that n, the value n also needs to be preserved in stack, right? So this is the complete assembly instruction, RISC-V assembly instruction. So as I mentioned, that the fact function needs to preserve, the fact function needs to preserve RA, the return address, and N, the argument of this fact function, right? So we need to require two word data, right? So the stack is adjusted as the -8, and then we need to store A0 in the stack. Okay, so arguments is stored, and then RA is also stored. Okay, and then when the function is returned, then the stack is just restored here. And then in the else statement, the else statement will, so this is the call, the function call, right? Okay, you can find that this is the JAL. So this is the function call, right? And then, this is the return statement. So what is required? So in order to perform return, so RA needs to be restored, right? We need to return to the caller, right? And also N is used here. So we need to restore N in this here, right? So we restore N and RA from stack. Okay, and then stack pointer is also adjusted, and then it performs the multiplication, okay, and return. So recursive function. So the recursive function looks special. It is because this function calls its own function. But we can apply the same approach to this recursive function also. So recursive function is the special non-leaf function, but this function calls its own function, right? So when we call another function, then RA, the return address needs to be preserved. And also required data. So what is the required data? And the arguments. So arguments also need to be preserved. Okay. So, but everything is okay. So everything is the other everything is the same. Okay. Okay. This is the factorial function. Okay. So let's see the how the stack is managed. Okay. So people call let us assume that the stack pointer is ff0, and then the recursive call, then stack pointer is adjusted, right? So you can find that in this code, you can find that when the fact function is called, then stack pointer is adjusted, right? Okay, so the firstly, the fact function is called, then stack pointer is adjusted, and then a0 is the argument of the fact function, and return address is stored, and then let us assume that the argument is 3. Okay, so because the argument is 3, then this value is larger than 1, right? So it will jump to the else. Then in the else statement, then in the else statement, fact function is also called. Okay, so the else, the fact function fact function is called here, right? So then it goes to fact function, right? Then stack pointer is also adjusted, and then RA is stored. Then what is this RA? So when JAL is executed, then RA is the PC of this instruction, right? So in the stack, the RA and then the PC of the load word is stored, okay? And then also the same, okay? So it's a A01. So, and then, so the stack is adjusted like this. And then, so because the argument becomes 1, then it will perform return 1, right? So A0 is 1, okay? And then we can return from this fact function. Then what is the return? So if you see this where is this one, okay? So you can find that this is the return, right? Then where can we return? So you can find that this is the JALR. It uses the return address, in RA. Then what is the return address? So you can find the latest RA. Okay. So if you can follow this factorial function code, right? So until this one, okay? So which code is executed? So this code is executed, right? JAL array fact, because the fact function recursively call its own fact function, right? So array is here. So array is the PC of the load word. Okay, the PC of this load word. So what does that mean? When we return from the fact function, then this part is executed. So you can find that in this part, you can find that the RA and N, the arguments are restored from stack, right? So here, and then stack pointer is also adjusted. So you can find the add SPSP 8. And then also you can find the multiplication. Okay, so and for the return, then this part is executed. Then the this stack is managed like this. So firstly, array is restored, and then A0 is restored, and then array, and then is restored again, and then A0 restored. Okay, so 2, and then this array is the array of the array when this fact function is firstly called, right? So do you understand? So it will return to the caller. Okay, so the stack is adjusted like this. So you may think that the recursive function is a little bit tricky, right? But actually, you can just understand the recursive function is the non-leaf function, right? And then the final step of the recursive function is the leaf function, right? So it's actually the approach is the same. So stack is adjusted, and then the required data is stored, and then also array needs to be stored. So that's what we learned in the previous class. Okay, so recursive can implement the recursive function like this. Okay, so you know this is so this is the so I frequently make the midterm question from this function, the recursive function, right? Okay, so but if you can understand how the non-leaf function works, then I believe you can also understand how the recursive function works. Okay. Okay, pseudo instructions. So pseudo instruction. So what is a pseudo? Pseudo means it's fake. Okay. So but it's not entirely fake. Okay. So pseudo instruction means that it's not run actual RISC-V instructions. So it means the hardware instruction is not defined, but we can frequently use this type of instruction. So assembly just supports these pseudo instructions, but pseudo instructions are translated into real hardware instructions, right? So those instructions are called pseudo instruction. Okay, so if you see this example, then you can understand. So if you read the RISC-V assembly code, then you can find these instructions like jump immediate, or jump and link the immediate, and then jump and link and RS and then return RET. But I already explained that RET, when in order to return from the function, we need to use the JALR0 array 0. Okay, so this is is equivalent to the 0 array. Okay, that's what we learned, right? So we can actually we need to use this instruction JALR 0 array 0, right? But it means return from the function. So instead of this real instruction, we can use the pseudo instruction RET. So RET is supported by RISC-V assembler, right? So which means that we can use. So RET works like this, but actually in real hardware, the instruction is translated to this real instruction, and then hardware just execute this instruction. Okay, so this is the example of pseudo instruction. Also, you can find the jump instruction. Okay, so it's just a jump. It's not jump and link. So what does that mean? We don't need to store RA, the return address. So actually jump immediate is equivalent to the jump and link 0 immediate. Why? 0 is not updated. 0 always has 0 value. Okay. So these are examples of jump instructions. Okay, and label. So also, when I showed the example of RISC-V assembly code, I used labels, right? And then I mentioned that labels are just, it indicates the program counter of the instruction, right? So for example, in this code, you can find the label main. So it means that it's the program counter of this instruction, right? Then also simple is the same. The simple is also label, and then also you can find that simple is the PC of the this instruction JALR. Okay, but in the hardware, so hardware cannot understand this text, right? So actually, this is just the assembly syntaxes, the RISC-V assembly syntaxes. Okay, so actually the labels need to be also translated in hard when the hardware instruction is generated, then labels also need to be translated. Okay, so actually, if you see the jump and link instruction, then jump and link instruction looks like this. Jump and link, and then RD. This is the destination register and immediate. Okay. So you can find that this is destination register, right? And then what is immediate? So we actually will already learned about the immediate value, like add I, right? Like add I. Add I has the immediate value. Okay. So I mentioned that this immediate value is the 12-bit signed number, right? But for the jump, this is a little bit different. But when we use the jump instruction, this immediate number is also signed number, but this immediate number is the 20-bit signed number. Okay, so it's a little bit different. But you can also understand that actually jump and link has the immediate number. Okay, so but then what does it mean? So you can find the jump and link, array, and simple. Then we can easily understand that, oh, if this jump and link is executed, then it will jump to this one. Okay. And what is this value? What is simple? So simple means just the offset from the current program counter. Okay. This is the program counter of this instruction, and then actually this simple represent the offset from current PC. So what does that mean? So actually, we need to jump to the 51C, okay? Then what is the offset? The offset means the difference between two values, right? So offset is the 0x51C minus, what is the PC? PC is the current PC is the 0x300. So 0x300. Then what is the difference? Difference is the 0x21C. Okay. So actually, it is represented like this. JAL, RA, and the immediate value. And then this immediate value is the 21C. Okay. But for this immediate value, we cannot use the odd numbers. So this is the condition. So immediate must be multiple of 2. Okay. For branch instructions and jump instructions, so branch instructions and also, you know, the branch instruction has the label, right? Like BQ, RA, X1, X2, and then label. So branch instructions and jump instructions include immediate value and the actual and the label, but these labels are actually immediate values. And then but the condition is that this immediate value must be multiple of 2. It should be even number. Okay. If we write the odd number, so it's incorrect, right? So I will explain later. Okay. So but not remember this. Okay. So the long jump. So not to so actually, so as I mentioned that so JAL use the 20 bits immediate number, and then JAL use the 12-bit immediate number. Okay. So then even though this is the offset from the current PC, then you know that we can jump to the very far from this current position, right? So then we can jump to uh then the offset may be, the difference may be very large. Then what should we do? So in order to support this operation, then RISC-V also supports the AUIPC. So AUIPC is the RD and immediate. Okay. So it means the add upper immediate to PC. Okay. So what does that mean? It just stores RD, the PC. PC is the PC of this AUI PC. Okay. The program counter, and then the immediate number is the 20-bit. So, but this immediate number represents the upper 20 bit. Okay. So actually we add the 12 zeros. Okay. So PC plus this immediate number is stored in RD. Okay. Then we can just implement the long jump like this. Like so AUIPC, RA, and then upper 12-bit, upper 20-bit, and then you can use the JALR. Okay. So because you know the RA is here and then RA is here. So in RA store the PC plus the 20-bit of immediate number and 0. And then actually for the lower 12-bit, you can find that RA plus immediate is also calculated here. Okay. So, and then you can jump to this PC. Okay. So actually these are two instructions, but we can represent these two instructions using also one line pseudo instruction like call. Okay, so call and immediate. So this immediate number is the 32-bit. So it's a very large number. But actually, this pseudo number, the call immediate, is translated into two instructions like AUIPC and JALR. Okay, so this is the long jump. So this slide shows the several RISC-V pseudo instructions, right? So you can find, so we already explained about the J and jump and J jump and JR. And then also you can find the move instruction. So what is move? It means the T5 S3. So actually we can move the data from a source register to destination register, but it's equivalent to this instruction. So it means in a RISC-V assembly code, we can use this instruction, this code, but it is actually translated into add I. So you can find the NAP. So, and then also I already explained about the NOT operation because the RISC-V does not have NOT, bitwise NOT instruction, because we can implement the NOT operation using exclusive OR immediate. And then NOP. What is NOP? NOP means no operation. So it does nothing. Okay. So you may think why NOP is required, but so when we if when we learn about the pipelining, so sometimes NOP is required. Okay, so NOP is just not just to consume one cycle, but when the NOP is executed, nothing happens in a CPU. So it's equivalent to add I 000. Okay. So and then also we already explained about the LI. Okay. LI is the LUI and add I. And then core is the AUIPC and then JALR. Also, you can find the BGT, BGEG. Okay, so we can uh, actually real hardware instruction is like this. Okay. The arrays. Okay, so we learned about the pseudo instruction and then arrays. So what is an array? So array is the group of the multiple elements, right? And then I believe everyone learned about the program language. So I believe you can understand about the array. And then actually we already learned how to access the element in array. Okay. So we can access the element in array using the index. So I is the index. So this is the index, right? And then by using this index, we can access the element, the data in this element. Then size of array is the number of elements, obviously. Okay. So this is the array example, and then I already explained that. But so when the array is allocated in a memory, then the arrays are allocated like this. So array 0. So this is the first element of array, and then actually this is the base address, the base address of array. And then from this base address, we can just add the size of our element, right? So if this array is the int type array, then we can just add the size of int, right? So let us assume that this array element size is the 32-bit, it's a 4-byte. Then the address of next element is the base address plus 4, right? And then the second element is the base address plus 8. Okay, that's what we learned. Okay, the arrays are allocated in memory like this. Okay, so when not access the array, then we can so this is the example. So we can just access the array using the like this. Okay, so firstly, the base address. The base address is stored in a certain address, and then the base address, using this base address, we can access the array element. Okay, so you can find the offset here. So this is the C code, and then not access the array 1, then the offset. The offset is added in the load word. Okay, it should be SLL. So this is another example. Okay, so this is the loop. Okay, so iterate the loop, and then so you can also find that the byte offset is just calculated here. Okay, and then it is using this byte offset that we can access the array element. Okay, so you can just understand that and understand how the array data is allocated in memory. Okay, you can just understand this, then you can access the element in arrays. Okay, so this is some miscellaneous topics. The ASCII. The ASCII is the text data. So in order to represent the text, then we can use the ASCII code. So it means that the text data can be represented using the byte data. Okay, using the ASCII code. So this is the ASCII code. Okay, so it's a somewhat it's not a important topic. It's just so it's some miscellaneous topic. Okay, so then let's see let's learn about the array and pointer. Okay, so actually in C we can use pointer, right? So actually the pointer is is a somewhat actually C is the somewhat low level language. So C has the pointer type. Then and then but I mentioned that you can understand the pointer like address of a variable. Okay, so as you can see, so we can also access the the element in memory using pointers, right? In C, right? So which means actually we can also access the array element using pointers. Okay? So pointers correspond directly to memory address. Okay, so let's see the example. So this is the two function, and then as you can see, these functions just initialize the array element, right? And then the left side code is the array type code, and then the right side code shows the pointer type code. Okay, but actually the function is the same. So in the left side code, you can find that the index is declared here, and then using the index of an array, then we can access the array element. Then array elements are initialized as zeros. But how about the pointer version? So it receives the pointer, the base address of array, and then also you can find that the pointer type is declared, and then this is the start point of this pointer type, the pointer, right? So this is the base address of array. So it is the address. So this operator represent address, right? It's a pointer type address, a pointer type operator, but this represent the address of this data, right? So address of the first element, this is the base address, is stored in pointer, and then pointer is just less than the size of array. It should be less than this one, and then pointer is increased. So what does that mean? So pointer represent just address, okay? And then we just increase the address of this P. So even though but it's a little bit different because this is the pointer type, and then as you know, this pointer type is the integer pointer type, right? So that's why you can find the P equal P plus 1. But actually in address, it's like the address plus 4, okay? Then we can directly translate this version and this version, okay? So this is the array version of this code. So I mentioned that this is directly translated, okay, without optimization, right? So this is the code, and then this is the code. So what is different? So the codes are different, obviously. Then which is better? So you may think the codes are different, obviously, right? But I asked that which code is better considering performance? Left one? Array version? No? Pointer version? Right. Pointer version is better. Why? So you need to explain. Oops. So what is the performance equation? So actually execution time, instruction count, CPI, TC. But if the hardware is the same, the TC is the same, and then let us assume that the CPI is also the same. Okay. Then the execution time. Execution time is proportional to the instruction count. So what does that mean? In order to reduce the execution time, then we need to reduce the instruction count. So instruction count in this example represent the how many instructions are executed by CPU. Okay? So how many instructions are executed? It is firstly this one is executed, and then if the array size is 100, then this amount of instructions are repeated 100 times, right? So it means it has the 5 multiplied by 100. So totally the instruction count is 501, 501. How about this code? It has the 3 initial code, and then also loop has 3 instructions. So it's a 300, 3 multiplied by 100. It has the 303 instructions. Okay, so if we just compare the instruction count, then this version is better when we consider the performance. Okay, so actually the compiler applies the compiler optimizations, which means that firstly we can reduce the instruction count. Okay, then we can also improve the performance because the performance equation looks like this. So it's this is execution time equation, right? So this code is better. Then do we need to use pointer? So the pointer is a somewhat tricky concept, and then also the problem is that when we use a pointer, then we can make bugs, right? Sometimes we can make bugs, right? Because in C, so using a pointer, then the C can access some other addresses. Okay. Actually, we need to check the range of array, right? But problem is that so if you are interested in the security, the CPU security, then the Spectre. So I believe you may have heard about the Spectre, but the Spectre attack exploits this range check statement. Actually, is because so the problem is that the pointer is tricky, and then also the problem is that we can make bugs when we use our pointers. So it's kind of uh, it's kind of dangerous, right? So that's why recently the U.S. government prohibit the using C, right? So it is because the C is the low-level language, and then the C has some vulnerability in the memory access, right? But you need to understand the C. So C is the basic programming language, okay? And then also, in order to understand the hardware, so like a computer system, then also you need to understand C, okay? So do we need to use pointer? It's actually not, because we can rely on compilers. Okay, compilers just analyze the code, and then compilers will generate the optimized code. Okay, so it's important, better to make program clearer and safer. Okay, so you don't need to use pointer. Okay, but you need to understand, even though we do not use a pointer version, but you need to understand how these pointers are translated. Okay, but just remember that better to make program clearer and safer. Okay. Okay, so we learned about the RISC-V assembly instructions, and now so we will learn how the machine language is translated from assembly instructions. Okay, so what does that mean? So what? Oh, I cannot use this. So this is the example of RISC-V assembly instruction, but as you can see, these instructions are also represented using characters, letters, right? So computers cannot understand these assembly instructions. So computers can understand only digital data. So it means the binary data. So these instructions need to be translated into the digital data. Okay. So which means the assembly instructions need to be translated into machine language. Okay. So in this, so we will learn how the RISC-V assembly instructions are translated into machine languages. Okay, machine languages. So as I mentioned, computers can only understand ones and zeros, okay, digital numbers. And then, so the instructions need to be translated. And then RISC-V, the RISC-V defines 32-bit instructions. So what does that mean? It means the size of a single instruction is 32-bit. Okay, so every instruction. So we learned about add I, load word, store word, and then blah, blah, blah. There are many instructions in RISC-V, but these instructions are represented using 32-bit data. Okay, so and then 32-bit is the 4-byte, right? So that's why I mentioned that the instruction size is 4-byte, and then that's why when we execute the next instruction, then PC becomes the PC plus 4. This number 4 comes from this one. Okay. So simplicity favors regularity. So it means that all instructions are represented using 32-bit data. Okay. The CISC is different. So it means, so if you read the x86 ISA manual, then you can find that some instructions occupy 1 byte, and some instructions occupy 2 byte. The other instructions occupy 4 byte or 8 byte, blah, blah, blah. So the instruction length can be different. It's a CISC type instruction, but for the RISC type instructions, the instruction size is usually the same. I mentioned the usually because, so think about the ARM. ARM is also the RISC type instructions, ISA. Also, the size of a single ARM instruction is 32-bit. But ARM also supports the reduced type instructions. I call the thumb. Okay, and then thumb instructions have 16-bit data. Okay, so thumb instructions are represented using 16-bit data. Also, RISC-V has the reduced form instructions, and then like a thumb. Okay, so RISC-V also can have the 16-bit instructions. It's a reduced size instructions. Okay, but in this course we will not learn about this reduced sized. But so we learned that. So in today's class we learned that jump instruction has the immediate data, and then I mentioned that immediate data should be even number. Okay, it's a multiple of 2. But so I believe someone think that this is why. Because I mentioned that the PC is PC plus 4, so which means that for instructions will have the PC, and then this PC is the multiple of 4, right? Obviously, right? Because the PC, for the next instruction, PC is the PC plus 4, and then the size of instruction is 32-bit. Then you may think, why multiple of 2 then for the jump instruction? It is because this instruction, the RISC-V also has reduced type instruction, and then the size of this reduced type instruction is 2 byte. Okay, that's why for the jump instructions, immediate should be multiple of 2. So usually, if we just use the normal instructions, like 4-byte instructions, then immediate needs to be multiple of 4. But in order to support the reduced type instructions, then immediate should be multiple of 2. Okay? So this is the reason. Okay? Okay, but in this course, we will not learn about the reduced type instructions. Okay? But just remember that why this immediate is the multiple of 2. Okay? Also, actually the RISC-V has the 4 types of instruction format. So instruction format means that when we translate the assembly instructions into machine language, machine instructions, then we need to define encoding rules. Okay? So instructions are translated into machine code based on the encoding rules. Okay? So there are 4 different types of encoding rules. So R type, I type, SNB type, and UNJ type. Okay? Okay, let's learn about the R type instruction. So R type instruction, so this R represents the register type. So what does that mean? An instruction has all register operands. Register operands only. Okay? It means the R type instructions. So example is arithmetic instructions like add x1, x2, x3. So in this example, add instruction has 3 register operands, right? So it has only register operands. That's why R type, R is the register type, right? So if we see that this add instruction has 2 source registers, okay, RS1 and RS2, and then 1 destination register, RD. Okay, this is, 지워지나? 아니네. 안 돼. RS1, RS2 is source registers, okay? So this is the R-type instructions, okay? And then all R-type instructions have this form, okay? Instruction and RD and RS1, RS2. Then we need to translate this instruction into machine code, 32-bit machine code. Then how? So this is the rule. So this is the R-type instruction encoding rule. So you can find the OP, RD, function 3, RS1, RS2, function 7. So actually, so let's think about this one. Which instruction is required? In order to represent this instruction, we need to require RD information, RS1, RS2 information, and we need to identify add, right? So, and then in order to represent the register, then we can use the register number, right? Because the RISC-V has the register from X0 to X31, right? So we can represent the registers using register numbers. So how many bits are required for representing register? 5 bit, right? Because there are 32 registers, okay? So in order to represent this one, we require 5 bit, 5 bit, 5 bit, okay? Total 15 bit. And then we have 32 bits. So we now have the 17 bits, okay? So we can use these 17 bits for representing add, okay? So then this is how. So if we see the R-type instruction, RD is here, RS1 is here, and RS2 is here. And as you can see, these register numbers occupy 5-bit fields, okay? 5-bit, 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 okay? And then in order to represent instructions like add, we can use the OP code, function 3, and then function 7, okay? So, but OP code is used for representing operation code. So which means it is used for representing like the R-type arithmetic and or load type instruction, store type instruction, branch type, blah, blah, blah. So in order to identify the instruction types, we can use the OP code. And then for OP code, we can use 7 bits. And then other fields like function 3 and then function 7 are used for identifying add. Okay, this is the encoding rule of the R-type instruction. Okay, let's see the example. So this is the add S2, S3, S4, right? And then actually, this is the ABI name. So we need to change these ABI names to the register numbers, right? So this is the actually add X18, X19, X20. So these are numbers, okay? So we can just put these numbers to the RD, RS1, RS2, okay? And then the OP code of add is a 51. And then actually when the function 3 is 0 and the function 7 is 0, then it represents the add, okay? So this is the R-type encoding rule. So let's see another example, sub. So, okay, so the ABI names need to be translated, represented using register numbers. So it's 567, 567, and then OP code is the same. Okay, so for the sub instruction, sub is the arithmetic R-type instructions. So OP code is the same, but the function 7 is different. Okay, so we can identify sub instruction. So these are decimal numbers. So we can just represent the decimal numbers into the binary numbers, and then by doing this, we can make the machine code. So easy, right? So if we just know how the instructions are encoded, and then if we just understand the encoding rule, then the assembly instructions can be easily translated into machine code. So another type, I-type instruction. So what is I-type? I represent the immediate type. So example, add I, x1, x2, and immediate. So what is this immediate value? So I mentioned that immediate value is the 12-bit signed number. So 12-bit 2's complement number. This is RD and this is RS1. Okay, because so it used the immediate number, so it has only one RS1. Okay, so and then also we need to use the OP code and then function 3. So for the I-type instructions, RD is here and the RS1 is here, but there is no RS2, right? Okay, and then OP code is here and then function 3 is here. This immediate number is here. And then I mentioned that this is the 12-bit immediate number. So 12 bits are assigned to this part. Okay, so this is the I-type instruction encoding rule. So if we just see the postfix I, then we can know that, oh, this is the I-type instructions, right? So let's see the example. So add I, x8, and then x9 and 12. Okay, so s0, s1, is 12, but this is the ABI name, so it needs to be represented using the register numbers. So it's RD is 8, RS1 is 9, and immediate number is 12. Okay, we can just put these numbers and then add I. The OP code of add I is 19. And then function 3 is 0. So by assigning and then it can be represented using binary number. So it's a machine code. So another add I, so but immediate number is minus 14. So we can just put minus 14 here. But this is the 2's complement number, right? So we need to represent the minus 14 for 2's complement number, right? So it is a 1111110010. Okay. So then this is the minus number. And also you can find that load instruction here. So why? If you see the load instruction, load RD and immediate, this is the offset actually, RS1. So actually load instruction also includes RD, immediate, RS1. So the format is the same. It's the I-type instruction. Okay? But the OP code is different, right? Because this is the different type instruction. So this is the load type instruction. So OP code is 3. And then we can just put the values to the RD, RS1, and immediate. Then we can make the machine code. Okay? So if we just if we just know the encoding rule, then you can easily translate. And then S and B type. So this S represent the store, and then B represent the branch. Okay. So why is called the S and B type? Because let's see the store instruction. Store instruction RS RS2, RS1, and okay. If we see the store instruction, this is RS2, RS immediate, RS1. Okay, so store instruction reads to register data, right? Store instruction reads to register data. Okay, RS1 and RS2. So RS2 is used for reading data from register, and then RS1 is used for calculating address. And then how about the branch, like BQ? BQ, RS1, RS2, and label. Oops. Okay, but we learned that labels are represented using immediate number, right? So we learned in this today's class, right? What does it mean? Store instructions, branch instructions, both require two source registers and one immediate number. And then this immediate number can be represented using 12-bit data. Okay? But S-type and B-type are a little bit different, because when we represent the branch instruction, then immediate number of branch instructions must be even numbers, the multiple of 2. But for the store instruction, this immediate number can have odd numbers, right? So it's a different. So S-type, so this is the RS1, RS2, and then OP code, function 3, and then immediate numbers are split into 2 parts, right? And then the upper part is stored in the bin number 31 down to 25, and then the lower part, the lower 5 bits, are stored in number 11 to 7. B type is a little bit different. Everything is the same, but except the immediate number. So if you see that this immediate number, you can find that it's a little bit different, right? Okay. So this is SM, B type. Okay. So S type. So this is the RS1, RS2, and then the 12-bit immediate number. And then so this is the example. So example of store instruction. So it's the RS2. RS2 is a 7. Oh, no. This is the RS1. RS1 is 19. This is the immediate. It's the offset. Immediate is -6. So we can just put these numbers to RS1, RS2, and then OP code is 35, and function 3 is 2. But when the immediate number is assigned, so actually -6 is the 1111, 1111, 1010, right? But the first 5 bits needs to be assigned here, right? And then the upper bits needs to be assigned here. Okay? So this is the store instruction. So you can, it looks like this. P type is like, looks like here. And then also we can apply the thing. But I think we need to explain about the P type in the next class. Okay. Okay. I will stop here. And then thank you for your attention. See you in the next class. 감사합니다.